Hello everyone, welcome back to my YouTube channel Learn with Sumi. In today's video, we are diving into an essential concept in vector calculus, the vector differential operator, also known as del or Nabla. Okay, and represented by a symbol like this. It looks like upside down triangle. Okay, the reverse or upside down triangle only. Okay, this is read as, or it is pronounced as, or said as del or Nabla. So let's break it down step by step, and we will also look at a real world example to make it crystal clear. Okay, now let's go into the definition. The vector differential operator is a symbolic vector, okay, that operates on a scalar or vector field. It could be a scalar or a vector field. It operates on both, and it is written as del equals to I times partial by partial x, sorry, this is an ant, okay, plus j times partial by partial y plus k times partial by partial z. Also, you can read it as dou by dou x, dou by dou y, and dou by dou z. I times dou by dou x, j times dou by dou y plus k times dou by dou z. This symbol represents the partial differentiation with respect to x, partial differentiation with respect to y, and partial differentiation with respect to z. I'll tell you how the partial differentiation happens with a real-time example, as I mentioned in the intro of my video. Okay, here this I, J and K, this I, J and K are what? What are these things? These are the unit vectors. Unit vectors. Okay, I, J and K are unit vectors. So here I is along with x, and j is along with y, and k is along with z direction. These are the directions x, y and z. So I unit vector is along with x direction, j unit vector is along y direction, and k unit vector is along z direction. And now when I'm talking about dou by dou x, dou by dou y and dou by dou z, they are the partial derivatives with respect to x, y and z. Okay, these are the partial derivatives with respect to x, y and z. So this operator helps us to define important operations like gradient, divergence and curl. So we will see what is gradient of a scalar field. For example, temperature. Okay, so when I'm talking about a temperature, let me consider del T. Okay, so del T gives me a vector that points to a direction of maximum rate of change of temperature. Maximum rate of change of temperature. And when it comes to the divergence of a vector, consider a fluid flow. Okay, that is del dot F, fluid flow. Okay, this tells us how much fluid is expanding or compressing at a point. So this is maybe if you're in initial days of your engineering, this might be a little complicated for you to understand, but it's totally fine if you're in the higher studies or you're specializing into the mathematics or the physics field. So it will be easy for you to understand. I'm just giving for the introduction so that you will have these points in your mind when you go much detail about these studies. And when I spoke about curl of a vector field, it's nothing but a rotation of fluid. So that is del cross F. I basically want to tell you that it can be operated with dot, cross, anything, right? It's a scalar, it's a vector. It can be operated with any of these fields. So del cross F, this is a measure of rotation or swirling of a field. Okay, so this gives that. So let me consider one scalar function. Okay, for example, just to explain you, let's consider a scalar function. F of x comma y comma z equals to x square y plus yz. Okay, this is a scalar function I'm considering. Now I'm going to find the gradient of f. Gradient of f. So let me use the different pen to find the gradient of f. So that is going to be del f equals to I times differentiation, partial differentiation of f with respect to x. Okay, plus j times partial differentiation of f with respect to y, plus z times partial differentiation of f with respect to, sorry, this is what, I, j and k, right? K with respect to z. I hope it is clear till now. Now we will differentiate partially with respect to, we will differentiate f partially with respect to x, y and z. So you will understand what I am really trying to say. So let me start here. First what I'll do, partial differentiation of f with respect to x I will do. Okay, so this is the equation I have. So I'm just differentiating with respect to x. I will consider all other as constant. How you used to consider the constants, I'll consider all other as constant. So partial differentiation of x with respect to x, f with respect to x, that is going to be only, this is what I'm going to differentiate, 2x, right? 2x. And as it is multiplied by, any constant multiplied, you write it as it is. So that is going to be 2xy. Okay, plus this is a constant, you don't have any x here, so this is going to be 0. So that's it. Now partial differentiation of f with respect to y, we will see what. Here I have y, so differentiation of y with respect to y is 1, right? So only x square plus partial differentiation of yz with respect to y, it is going to be, y is going to be 1, so z. That's it. Now partial differentiation of f with respect to z. Now you don't have any z here, any z term here, so this is going to be 0, this is going to be 0, plus this is yz partially differentiated with respect to z, so this is going to be just y. Right, we got it, we got all the three values, these three values we got it, right? Now we will simply substitute in this. Okay, so del f equals to, or Nabla f is equals to I times 2xy plus j times x square plus z plus k times y. So this vector tells us how f changes in space, how f is changing in space. Okay, and that's a quick overview of a vector differential operator, a powerful tool in physics and engineering. If you found this video helpful, don't forget to like, share and subscribe for more math and science content.